Okay. So one of the problems was that suppose you are given two algebras
Okay,
and
sir.
you have to see whether their Cartesian product was an algebra. Or not.
Okay, sir.
So let me write it here again. Suppose f and g are algebras. We want to know if f cross g is an algebra. And we already saw that if they were semi-algebras, this is true for when f and g are semi-algebras.
So what is semi-algebra? Like ring? Uh,
Yes, not like ring. Okay, let me just go through the definitions.
okay, okay. Because in
So,
that course we didn't see this term.
okay, no
They
problem.
used a term
So,
for ring and algebra. So ring is wherein you have basically
yeah,
countable.
perhaps,
Sorry, not countable. Finite union differences. Uh, yeah, finite unions and differences that defines ring. So sigma ring is if you extend to countable union, and algebra and sigma algebra are corresponding versions wherein they also have the full set, uh, which
uh,
includes complement.
so here semi-algebra requires that the complement can be written as finite unions of the elements. So, suppose we have a collection in the power set. This is a semi-algebra. If first is empty set and whole set belongs to C. Second is whenever A and B they are in C, this implies that A union B is in C. And the third thing is that if A is in C, this implies A complement can be written as a union of AIs, I running from 1 to say some M, where all these AIs belong to C and they are pairwise disjoint.
Okay, okay, okay. Okay, so this is
So yeah.
disjoint
So
union.
first,
Okay.
yes. A first example of a semi-algebra is just look at this collection: empty set and power set, empty set and whole set. So this is automatically a semi-algebra,
Okay, I
right?
see.
Because by definition, empty set and X is in C. Whenever A and B in C, they're unions. So there are only two possible unions, right? Either you take empty with empty, X with empty, or X with X. So
Right.
everything is in X. And the complement again, empty set complement is X complement is empty. All these
Right.
three are set.
So if we fix that, like if m was equal to one, like if it was union of only one set from our like from our whole collection, see, then it would be a full algebra. But here
Right,
you are
right. If M was
generalizing
one,
it.
then correct. If M is one, then it is a algebra.
Okay. If m is one for every such a, like every such
Correct.
a, for every such a in C, we have a complement equals some AI for AI AI in C, then it would have been an algebra. Okay.
Yes. Because see, if M is one, then what we are saying is A complement is inside C, right?
Right. So this is
And then
something
one,
more general. Like,
yes. So this is weaker than algebra.
yes.
One more example which we saw during class was this. Look at all intervals in R. Then this is a semi-algebra because complement of an interval is actually union of two disjoint intervals, right?
Right. Right.
Okay. Oh, I sorry. There
No,
is
but
a
if you
small
have union,
yeah,
the second
small
property.
mistake. Yes. There is a small mistake. I meant to say intersection, not union.
Oh, okay.
Yeah, yeah. I'm really sorry about it.
Ah,
What I
no,
meant
no,
to
no,
say is
I see.
whenever A and B
I
is in C, A intersection B is in
I see.
C. Okay. So and then one of the problems that we discussed in the previous class was this, that if F and G are semi-algebras, then their Cartesian product is a semi-algebra. And then I gave one exercise that whenever F and G are algebras, whether their Cartesian product is an algebra. So, what do you think? Is it going to be an algebra?
Yeah, like empty set will definitely belong. And
Okay.
if I take basically two different sets in F cross G, in the Cartesian product,
Mm-hmm.
and and basically, if I consider their union, that uh,
So
yeah,
that union might
yeah,
cause problem.
union might not
Uh,
be.
so the complement might cause a problem. Right?
Yes, yes, it doesn't seem.
So to get a counterexample, okay, has anyone tried getting a counterexample? Actually, I gave that hint only that last time I said that the complement is the union of certain things. Therefore, the complement need not be inside the F cross G. So has anyone tried getting a counterexample? Okay. If not, let us see. So what we'll do, let us look at the algebra of the maybe write it. Suppose this is the algebra. Look at all these finite unions, IIs. II is an interval in R. So, okay, this was also discussed in one of the lectures that this is actually a algebra. Let us look at F cross G. Then F cross G by definition is union I from 1 to n II cross union say K from 1 to m JK, where IIs and JKs they are intervals of. So does everyone agree with this?
Yes, sir.
Okay. So now just let us look at what type of sets are there. If n and m are 1, then basically we have all the rectangles inside F cross G, right? So sets of this form are definitely inside this F cross G. Now the thing is, what about its complement? If you look at the complement, then the complement basically can be divided into these sections, the other infinite rectangles. The question is whether these infinite rectangles, this union, whether it can be written as a Cartesian product of two sets or not. So now that is the question. Question I cross J complement, whether this is equal to union of IIs cross union of JKs. 1 to n and j from 1 to n. Okay. So what do you think?
No,
Why?
because if we cover all points on x-axis and if we have to cover all points on y-axis, then we'll essentially get whole r square.
Correct. So the problem with this is that suppose you take a point here, let us call it x1, y1, and let us take a point here, x2, y2. If this can be written as a Cartesian product, notice that this y2 is inside this set, and this x1 is inside this set. So x1 comma y2 is here, but that cannot happen together. Right? Yeah, please unmute. I mean, please mute yourself. There is some noise. So the idea is that suppose I can write I cross J complement as some A cross B, where A and B they are coming from us. Then what will happen is that let us look at these type of elements x1 y1 in I cross J complement such that y1 belongs to J, and let us look at x2 y2 in I cross J complement such that x2 belongs to I. But once this happens, this means x2 y1 must belong to I cross J, and yeah, then what is the issue? Yes, at the same time, this y1 also belongs to B, y1 belongs to B, and x2 belongs to A. implies that x2 y1 belongs to A cross B. But A cross B is I cross J complement. So this cannot happen. This is a contradiction. Is this fine with everyone?
Yes, sir.
Okay. Sashikant, are you there?
Ah, yes, sir.
Okay. So this is fine, right?
Yes.
So I have actually skipped some parts. You can try writing the in between, argue all the arguments. So now let us move on. Sashikant, you had some doubts from the lecture. You had mailed me. Can you just explain what are your doubts?
That monotone class theorem, uh, the when usually M of C is some algebra, then let's say A is some algebra, M of A is subset of S of A. That is whether
Uh-huh.
it is a collection is algebra or not, that would be valid. But for the other way around, if A is algebra, then in the proof of S of A is subset of M of A, we have to prove that M of A is a monotone class. So
So you are
we,
talking about this result, right? That I have written. If
ha,
A is an algebra, then monotone class generated by A is equal to the sigma
yes.
algebra generated by A.
So while proving S of A, S of A is a monotone class service taking L of F. L of F is like fix some set F from monotone class and then collect
Ac-
all the possible unions from X
Yes.
and then
So we,
show
we
that LFF is like a set of all sets such that F union A belongs to M of A.
Mhm.
Uh, so it shows that actually the closure under unions, closure for unions, there I
So
didn't
Acha,
understand much
just a
actually.
minute. Is it clear that L of F itself is a monotone class?
Union, I was having doubt.
Union you were having doubt. Okay, so let us take an increasing sequence in L of F. So let an be an increasing sequence in L of. What does it mean? It means that an is contained in an plus a for every n. But what does this mean that it is inside L of f? It means that an union f, this is in M of f, correct?
Yes, yes,
Okay. But then since an is an increasing sequence, can I write an union f is contained in an plus 1 union f?
yes,
Okay. But once this is true and M of a is a monotone class, so all these unions, an union f, this is inside M of a.
yes.
But this union is what? This is just this countable union of ANs union with F, isn't it?
Yeah, yeah. But
So
after this, I
there,
was taking L of F is a monotone class again. He will be showing after the proof some L of F, which I have sent you in email.
so okay. So similarly, you can prove for intersection also, right? That it is closed under
Yes,
decreasing
yes,
intersections. Okay. Therefore, we have LF is a monotone class.
yes,
Is a monotone class for any L. Okay. Now, what we want to prove? We want that A should be contained in L of F, right? This is what was the goal.
yes.
Okay.
But
So to
then
prove
F
this,
is different. F is different, and then if I usually if I think for proving this, I will take a set from A, and I have to prove that that set also belongs to L of F. But actually,
correct.
survey was slightly bit confusing. I did not
The
understand.
notations might be a bit confusing. So let me just write down what happens. Suppose that f this f initially comes from A. Suppose F comes from A, but A is contained in MA, right?
But then LFF we defined it by fixing F from M of A, not from A.
Yeah, correct, correct. But I can always choose F from A also, right? Just wait for some time. We will reach to M of A.
Okay.
Since A is contained in M of A, I can choose this F from A. Is that fine?
Yes, sir.
Okay. So choose this F from A. But then what is L of F? L of F by definition, it is collection of all those subsets whose union with F is in M of A. Okay. Now let us take E inside of A. Can I say that E union F is again inside A?
Yes, by union property of.
Because A is an algebra, right? So the unions must be inside A. But A is contained in M of A. So does this mean that A is a subset of L of F? Can I say this?
Provided we take F from A, then it is fine. But F
Yes.
from
So
M of A, we don't know.
just again notice that I have assuming that F is coming from A. Okay, here I have assumed it. For the time being, let us assume this.
Yes,
Okay, so this is true. And therefore, what I have proved is whenever F comes from A is contained in L of. This is what I have proved. Now, what I know is, or rather, what we should observe is that if a set E is contained in L of F, this happens if and only if F is contained in L of E. Is this observation clear?
yes.
Now, so let us, what we now want. We want that this M of A basically, just a minute. Yeah. Okay. So for any F in A, we have A is contained in L of F, implies that M of A is contained in L of F, right? Because M is the smallest monotone class containing A, L of F is a monotone class containing A.
Yes.
Is this also fine? Okay. Which means what? For any F in A and any E in M of A, E is inside L of F, right?
Yes.
Okay. But I have just seen that whenever E is inside L of F, it is the same as saying F is inside L of E. Therefore, for any E in M of A and F in A, F is inside L of E. Sorry. Is this clear?
But this quantifier stuff is slightly confusing for all E in M of A and for all F in A. I mean, for
Okay.
all E, there exists F for like for all and for all, or for all
No, no,
for exist.
for all, for. So see, even if I write it like this, it is not really going to make a difference here. And E in M of, correct?
Yes.
So what we are saying is you take any E in M of A, every set inside of A is contained in L of E.
But then, okay, okay.
That is what I wanted to
Because we
prove.
use it that green color, that the star property, we are just switching the
Ah,
variables.
yes. So this is really important. This is an important observation that the way we have defined L of F if a set is inside L of F, then F is inside that L of that set.
And one set we choose from A and another from L of F.
No,
And for L
one
of
set
F,
we choose from A, another set we choose from M of A.
from that L of F, right? F belongs to A and then E belongs to L of F.
No,
The
E
star property.
belong.
F belongs
Ah,
to A, then we choose
yes,
E
yes.
from L of F. Then only we can switch. Then E
See, this
comes
switch
from
is true
L
for
of
any E and F, right? This switch is true for any E and F.
yes. But yeah, I understood. I will think about it again.
No, no. If you have any more doubts, you can clarify right
Actually,
now.
I was just thinking E has to come from M of A. E
No,
belongs to
see,
yeah.
this star property, does it really involve any property of M of A or A as such? No, right?
No, no,
All
no.
we are saying is
Yes,
see L of F. Whenever I say that E is in L of F, by definition, E union F is in M of A. But if E union F is in M of A, then F union E is also in M of A. So F belongs to L
yeah,
of E, and then the other way around, I think.
understood. Actually, that star property is the key here.
Yes, yes. So it is tricky, and also this is independent of whether or not this F comes from A. Okay. Okay.
Yeah,
So
we
is
are
this
just
fine?
switching it. Yeah, understood.
Hmm.
And one more question. I was
Uh-huh.
asking about that hierarchy, right? Semi-algebra comes at the top, and then subset will be algebra, and then again its subset would be sigma algebra, and again its subset would be monotone class, right?
Not exactly. Actually, what we have. Uh, so let us look at this. Yeah. So semi-algebra. Then we have
So
algebra. Wait. Algebra. Then we have sigma algebra, and then we have monotone class. Okay. So we have seen that algebra, all algebras are semi-algebras, right?
yes,
And all sigma algebras are algebra.
and again sigma algebra is a monotone class.
Yeah, all sigma algebras are monotone classes. But if we want the reverse implication here, we can go from this to this, provided
Algebra,
we have both of them,
collection
right?
algebra.
Yeah. So what we have is the biggest one is the semi-algebra. Then inside we have algebras. Somewhere maybe like this, we have monotone classes, and these are our sigma algorithms. Does that answer your question?
Sigma algebra is intersection of algebra and monotone class, is it?
Yes,
No, no.
because
Sigma algebra is one set and algebra is another.
algebra. So okay, I should have made it in some different color. So see, this blue one is the algebra. Okay,
Okay.
this is the algebra, and this inside this this part is sigma algebra. Only this part.
Okay, it comes in the intersection of algebra and monotone class.
Right, because every sigma algebra is an algebra, every sigma
Yes,
algebra is a monotone class. And whenever we have something which is both an algebra and a monotone class, it is a sigma algebra, right?
yes.
So it is exactly the
Suppose,
intersection of algebra and
yeah. Suppose I have a collection which is an algebra, then I generate a sigma algebra out of it. I mean, I will generate a subset. I will generate a subset class from higher to lower. I will take a collection from the higher class. I will generate a uh, collection of the lower class. I mean subset. Would that lower subset would inherit the properties of the higher subset? Say for
yes.
algebra, it should,
See,
right?
because sigma algebras are already algebras, right?
Yes.
It will inherit.
Okay.
Any other questions from whatever content is covered? No? Okay, so let us really look at through. There are some questions in the assignment that involves limit supremum and limit infimum of sets. So, okay, do you people know what is limit supremum and limit infimum of real numbers?
Yes, sir.
Do you know it?
I think, sir, limit supremum is plus infinity.
No. Why is it
Among all
plus
the upper
infinity?
bounds, take the
The
lowest upper bound.
it's the limit of the supremums of subsequences after n. So like if
Correct,
it's
correct.
the
So,
supremum of like
First,
supremum,
we take supremum from a sequence.
then take the limits of that. Like it's a monotonic sequence, so it will have some convergence. Like either it
yeah,
will converge to infinity or minus infinity, or it will converge to a finite value. So, but it will converge.
correct, correct.
It's a decreasing sequence.
Yes. So, given a sequence in R, the lim sup of an, so we usually write it like this. It is read as limit supremum. This is defined as the infimum over all of n of this set. Look at the supremums over m bigger than n, AMs. So what it is saying is that after a certain stage, look at the supremum. That will give you another sequence, and the infimum of that sequence is the limit supremum. And similarly, the limit infimum, an, this is the supremum of all infimums. So now the question is, how do you know that this infimums of supremums and supremums of infimums exist? So perhaps that I leave it to you as an exercise to prove that these sequences are actually monotonic decreasing and monotonic increasing. And in fact, this can be found in any analysis. Prove that this sequence supremum of m bigger than or equal to n am, this is a non-increasing sequence, or sometimes it is called a decreasing sequence. And infimum of m bigger than or equal to m am, this is a non-decreasing sequence, or increasing, whichever terminology you are familiar with, you can use. Okay. Now these are something about real numbers. What we want to do is we want to define lim sup and lim inf of sequence of sets. So the definition is as follows. So let En be a sequence of sets. Sequence of sets. Then limit supremum of En. This is defined as the intersection over all n. Look at unions over m bigger than or equal to n of Ens. And similarly, lim En, this is defined as the union over all n's, intersection from n to infinity En. So is the definition clear? Yeah, please respond.
That inner bracket is m equal to n to infinity. So
Yes,
En is
inner
an
bracket.
increasing sequence.
En
Union
is
of
an in,
union of En is an increasing sequence.
no. Union of E, actually this is En, not En. So
Union of
see, En. So notice that if I look at this union, m from n to infinity En, and union m from n plus 1 to infinity en. Then which one is contained in the other?
Second one is contained in the first one.
Correct. So this is actually a decreasing sequence.
Okay, okay, understood.
And
Then
similarly
after
here,
that,
if
you are using intersection n belongs to n.
correct, correct. And similarly, if I have this, then which one is contained in the other?
First is contained in second.
We have this. So this is an increasing sequence. And then we are taking the union of an increasing sequence. Okay. So see, unless we have really either a sigma algebra or something, this sequence of set from a collection need not have its lim sup or lim inf inside the same collection. Okay. So one of the crucial observations is that if C is a collection of subsets, then lim sup and limit of a sequence in in C need not be in C. And I guess you can really find some counterexample. So something which is not a monotone class, and particularly this one will cause a problem because an increasing sequence will not have the intersection, or a decreasing sequence will not have the union, or the other way around. I'm interested. Decreasing sequence will not have the intersection inside C, or increasing sequence will not have the union inside C. Okay, so there are some equivalent ways to write this lim sup and lim which we would like to see right now. So these ways are this. So lim inf en, I can write it like this. Collect all those x such that x belongs to all but finitely many ens. To all but finitely many ens. Okay. So what does this mean? Can someone tell me? To all but finitely many, what does this mean?
Belongs to countable infinitely many ens.
Yeah, definitely infinitely many ens, but all but finitely many means that up to certain stage x may not belong to ens, but after that stage x belongs to every en. Vishal, do you want to say something?
Yes, sir. I think it means X will be in almost all ens except finite. Uh,
Correct, correct. Yes. So x will be in all of the ens except for finitely many. So it means that there is some n naught such that for every m bigger than or equal to n naught, x belongs to en. Now, can we quickly prove this? So let us begin. So I will write, keep the definition of lim inf here. So let us take x in lim inf n. What does it mean?
Like it belongs, so there exists some n such that it belongs to intersection of m equals n to n.
Correct. There is some n such that x belongs to this intersection. But what does this mean?
That it belongs in all of these EMs for m greater than equal to n.
Correct. It means that x belongs to for every m greater than or equal to n, x belongs to en. Now, uh, can you give me a similar definition for lim sup?
Yeah, so basically x, like for all n, there exists an
Uh-huh.
m where x, there exists an m greater than equal to n, where x belongs to em. Like it keeps on recurring infinitely.
Correct, correct. So Can I write it like this? Lim sup En can also be defined as collect all those x such that x is in infinitely many ens.
Yes, 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 yes. So
So
limit
again the
is
same thing
set of.
because no, I could not understand. Could you repeat?
I was saying that limin will be a subset of lim sum. Like in real
Oh
numbers, we
yeah,
have
that
limin
that
less than equal to lim sum. So here it will
right, right. That will come to later. Okay, but yeah. So you are correct. Whatever you are saying is correct. But we will come to later. Let me just write this. So this means for each n, x belongs to the union of m from n to infinity en. But this is same as saying for each n, there exists some n m bigger than or equal to n such that x belongs to en. So, please read this m everywhere. Okay. Okay. So now actually Dheeraj told us that we should expect that lim en is contained in lim sup en. So this is our claim. So do you people agree that this should be true?
Yes, sir.
Okay. Why do you think this should be true?
Actually, X is in almost all the ENs in the union
Uh-huh.
part, and
Uh-huh.
in the intersection part, there uh, we may find some ENs in which X will not be. We may find ENs in which X will not be the part.
Okay, but
Am I right? I don't know. Sorry.
I actually could not understand what you said. See, you are saying
Sorry.
that X is in almost every EN except for finitely many. That's what you are saying, right?
Yes, sir. The
But then how
union.
from there, yeah, from there, how did you conclude that it is in links? Yeah, maybe you can look at whatever you have done till now.
Soup says there should be some number beyond n for where x should belong to this, whereas the first one says it belongs to everything beyond some number.
Yes. So how do you relate this to?
We can take the maximum number out of these two and say maximum of left side and right side. Beyond that, left side part belongs to every ei, and right side part says if it belongs to only one sum j beyond I, beyond that
Uh-huh.
max number, then
Okay.
it should be
But
valid.
right, right. So that is one way. Can we not directly say whatever the characterization we just saw, if x is in En, then x is in every En except for finitely many. From there, can we not say that it is in infinitely many Ens?
Yes, intersection part of countably infinitely many subset of union of infinitely many.
Exactly, exactly. So directly from these two characterizations, we can see, right? Does everyone agree? Right, please respond.
yes.
So now let us look at some examples like how to calculate these lim and lim sup of sets. First example, let us look at this sequence minus infinity comma 1 by n. So how does this sequence look like on the real line? So maybe we have 0 somewhere here, 1, and then there is half, there is 1/3, one fourth, and so on. Somewhere 1 by n, and the next one is 1 by n. So I'm taking open intervals. So these are all open and towards this. I want to look at lim sup en. So I know by definition this is equal to the intersection of unions, right? But what are these unions? Can someone tell me?
It will be like En only. So actually, in the first expression, it should have been Em, union of
Yes,
for
this should
every,
be en. Yes,
but it will equal En. This union will equal En.
yeah. This is equal to en, right? Minus infinity to 1 by n. 1 by n. Because all other intervals are actually smaller than this interval. Therefore, the union is the largest one. So now what about the intersection?
Empty
This
set.
is
Oh
basically
no, minus infinity to 0.
okay. So this is minus infinity to 0. Is 0 included or not?
Included, like it's closed on right side.
Okay. So let me ask you why.
Yeah, because 0 is strictly less than 1 by n for all positive
Yeah,
integers.
that is fine. So if I take any x less than or equal to 0, x is strictly less than 1 by n for every n,
Right.
which implies that minus infinity to 0 is definitely contained in this intersection. But why is it equal?
Yeah, because if it is strictly positive, then there is some n such that 1 by n is less than that epsilon. Like if I choose some epsilon strictly greater than 0, then there is some n where
Correct.
1 by n is strictly less.
So,
So it will be outside that en.
correct. If x is positive, then there is some n such that 1 by n is less than x. Uh, can someone tell me why?
That Archimedean property, like for every x we
Correct.
can find an n there where n x is greater
So
than.
this is due to the Archimedean property.
Otherwise, like intuitively, it's true, but formally through Archimedes.
Yeah. So mathematically, we should give the reason that due to the Archimedean property. What does the Archimedean property say? You take any real number and any positive real number x, then we can find a stage n such that nx is greater than the given real number, right? So let me just write it here. For any y in R and any x positive, we can find a natural number such that nx is bigger than y. So here our y is 1 and x is anyway given to us to be positive. Okay. So this is lim sup. What about lim in? Yeah. So by definition, it is this. Now, someone please compute and tell me what is this equal to. Perhaps I will write it. This is minus infinity to 1 by n.
Yeah, this intersection will be minus infinity to 0 closed for every n.
Correct. So this is minus infinity to 0. Using the same arguments, right? Using the exact same arguments, this is minus infinity to 0. So the union is again minus infinity to 0. Is this clear? Yeah, somebody respond?
Yes. Yes.
Other than you.
Yes, sir.
Em is minus infinity to 1 by m, is it?
Yes. So En in general was minus infinity to 1 by n.
Then is it the same thing which we considered in the earlier limb soup? I
That
mean,
is what
what's
the
the
conclusion is.
difference?
That in this case, lim sup and lim inf, they are the same. They are the same sets.
I mean, in the earlier case also, we took the intersection of all sets minus infinity comma 1 by 2 intersection minus infinity comma 1 by 3.
Uh-huh.
Is it? Uh, minus infinity
Yes,
comma.
yes. So see, lim sup by definition is what intersection of the unions, right? Yes.
Yeah, I mean, I'm not able to perceive the difference. I will think again. It looks
Okay.
fine for now.
Ah, okay, okay. So you go through this, and if you have any doubts, you can either mail me or ask in the next session. Let us look at another example. Suppose now I consider my En like this: 1 by n plus 1 to 1 by n. So, Sashikant, can you tell me how these intervals look like on the real line? So, suppose this is 0 and this is 1. Which is my first interval?
1 by 2, 1 by 1, 1 by 2 to 1, 1 by 3 to 1 by 2.
So, this is my E1, right?
Yes, 1 by 3 to 1 by 2.
And this is open. So, half is not included and 1 is not included.
Yes,
The next one is 1 by 3 to 1 by 2. So, the next one is this interval,
okay.
2. Again, it is open. 1 by 3 is not included, 1 by 2 is not included. And then, I just keep on doing this. This is my E3 and so on. So somewhere here 1 by n and somewhere 1 by n plus 1. This is open, this is En plus En. Now, again, what we want to know, we want to know what is its lim sup and what is its lim inf. So by definition, this is intersection of all n's unions from n to infinity En. Okay. En. So this is n from 1 to infinity union m from n to infinity 1 over m plus 1 comma 1 over n. Okay, so Vishal, can you tell me what is this union?
Uh, it will be, sir, I think 0, comma 1.
Do you mean to say this this is equal to open interval 0 comma 1?
1
You
by
mean,
n.
yes, sir.
0 to 1 by n.
Uh,
Like, because it's n onwards.
okay. Yeah, just a minute. Sashikant, what do you think?
1 by n plus 1 comma 1, but it has some holes at the
Do you mean to say this is equal to 1 by m plus 1 comma 1?
1 by n plus 1 comma 1. N
Yeah,
plus
n
1
plus 1.
comma 1 and then minus some rational points. Minus some rational points 1 by n, 1 by n minus 1, 1 by 4.
1 by n minus 1 and so on. Are you saying this?
Yes, I think. It looks
Okay,
like
why
I'm.
do you think that? Okay, just let us see here. Does half belong to this union?
No, right? It is an open set actually.
See, what union we are considering? We are considering unions
1
beyond
by
certain
3,
point.
1 by 3, 1 by 2, union 1 by 2, comma 1. So 1 by 2 will definitely be not there.
See, this union is
Actually, the unions are
one.
to left of 1 by n, but I will also remove those points of type 1 by k.
See, this is the union, right, Sashikant?
Yes, sir. 1 by n,
So
comma 1 by n minus 1. We are decrementing by 1 each.
No, why are we
One
decreasing?
by
We are
n plus one
increasing.
comma one by n union one by n comma one by n minus one.
No, but why are we decreasing that? And
Because it goes from 1 by 4, 1 by 3, 1 by 2, 1 by 1. So in denominator terms are decreasing. So n plus 1,
no, they are not.
n minus 1.
Okay. See, let us look at this thing. Union m from 1 to infinity em. This is union m from 1 to infinity 1 by m plus 1 to 1 by m. Right? So what is this? This is half 1 union 1/3 half and union so on. Correct?
Yes, yes.
Okay. So this is one thing. Now let us look at union m equal to 2 to infinity em. So notice that this is 2 to infinity 1 over m plus 1, 1 over m. So now this interval won't come, right? This is not there. This starts from 1 by 3 to half, and then the
Yeah, yeah,
next one
yeah.
is 1
Understood,
by 4
understood.
to 1 by.
Yes, yes. Yeah, fine.
So now can you tell me what is this union?
Yeah, it should be fine, right? 1 by n plus 1 comma 1 minus that points.
See, that is what I'm asking. So see here also. So you are saying that this should be equal to uh,
Sorry, the
this should
other
be
way
equal
around.
to
Minus
half
1
1.
by n plus 1, n plus 1. Like
No, no, no. Just repeat that again. I could not understand.
1 by n plus 1 comma 1 minus 1 by n plus 1, 1 by n. Sorry,
Okay.
I
So
am
let me ask you: are the points closer to zero inside this union?
yes,
Okay. And are points bigger than 1 by n inside this union?
bigger than 1 by n, is it?
I'm asking:
Yes,
are points bigger than 1 by n also inside this union? See,
yes.
let me write it in general, then perhaps you will be able to see. This is what? This is 1 over n plus 1 to 1 over n, union 1 over n plus 2 to 1 over n plus 1, union 1 over n plus 3 to 1 over n plus 2, and so on. Correct? Or perhaps if this is confusing, let me write it like this: 1 over n plus 3, 1 over n plus 2, 1 over n plus 2, 1 over n plus 1, and 1 over n plus 1, 1 over n. Now tell me.
Yeah, it looks like we are moving closer to 0.
Right. So, okay. In the figure, can you tell me? So, say this is 1 and this is 1
So,
by n. So, where should I draw my first
denominator,
interval?
denominator terms are decreasing, so we will be approaching the intervals towards 0.
Right. So, first interval, I will choose this, right? This is 1 over n plus 1.
Yes,
The next, I will choose somewhere here. This is 1 over n plus 2. And then so on.
yes.
What
So
is its union?
union would be 1 by m comma 1 by n minus that all this in rational points. So 1 by n, 1 by n plus 1.
Not 1 by, see, m won't be there, right? It will be 0 to 1 by n minus these rational points.
Ah, agreed, agreed.
1 by n, difference 1 over n plus 1, 1 over n plus 2, and so on.
Provided
Yes.
again we put yes.
Provided what?
No, sir, it's fine.
Vishal, did you understand this?
Yes, sir. Yes, sir.
So, neither of these two answers. This is also wrong. This is also right. Fine. So this was the union. What about now its intersection? So we want to ultimately find n 1 to infinity union n from n to infinity en. So this is intersection n from 1 to infinity 0 comma 1 by n difference this and so on. So what do you think?
Empty set.
Yes, Guru. Empty sets. Okay, so let me ask why.
Because so if anything belongs to this intersection, it must belong to each of the sets. And if we have anything which is less than equal to zero, that definitely is outside. That's not in any of these sets, so that's not an intersection anyways. And for anything which is
Right.
strictly greater than zero, we can find at least one n where it is outside 0 to 1 by n. Yeah, so there is no point in this intersection.
Correct. So the thing is, if x is less than or equal to 0, implies x is not in 0 comma 1 by n for any n, which implies x is not in this intersection 1 by n plus 1. And on the other hand, if x is positive, this implies there is some n such that uh, 1 by n is less than x. But then this again
Uh,
implies x is not in this intersection, right?
Sir, can we take n tends to infinity? Then we will get 0 comma 0 open set, open interval 0 comma 0.
But
As a
that's
But we
like
cannot really take limits inside.
no,
Actually,
like
that part I am going to come to
open
it.
interval. Like if we have open interval a comma b, that's non-empty only if a is strictly less than b. So like even if you say like open interval 0 comma 0, that's also
Hmm.
empty.
See, that is what I am saying. First thing is, I cannot really make sense of this thing, right? Because I don't know how to define this. Sashikant, do you want to say that these two sets are equal?
I was thinking, but since you are saying maybe there is some wrong, something wrong.
No. See, the thing is,
I was
there is
thinking in the
something.
same way.
No, no. There is a concept of defining limits of sets. The only thing is that we have not seen it yet, so we cannot use this. For me, it does not make sense right now. Did you get my point?
Yes, sir. Actually, I applied it to the inside.
Ah. So what we need to do is we need to do some analysis to prove this. Okay. So whatever Dheeraj told us is correct. That we can use the Archimedes property to conclude that positive numbers are not here and non-negative, non-positive numbers are anyway not here. So this is empty. So what we concluded is lim sup of ens, and what was my en? 1 by n plus 1 to 1 by n. This is empty. Okay. What can we say about lim in?
That is also empty.
Why?
Because it is a subset of lim-sup we have seen
Correct.
earlier, so it has to be empty. And otherwise, like even if we go by the like the definition of limit, so it will be unions of intersections, but each intersection by itself is empty. Like intersection of n
Right, right.
equal to m, em, that's
So you can go both ways. That is fine. So, but the easier way is that we have already proved lim is a subset of lim soup, and once lim soup is empty, there cannot be anything inside lim. It would be a contradiction. Okay, is this fine? Yes, Sashikant and
Yes,
Vishal, is this fine?
yes, yes.
Okay.
Yes.
Now, coming to this, actually, I was going to talk about this, but not in terms of limits, rather in terms of lim soups and lim. So, let us look at a question, or rather, just a
Sir,
curiosity.
actually, if we see the diagram,
Uh-huh.
intersection would be very, very tiny small part around zero. So it should be one by some huge number. Zero comma one by
Which
some huge number.
which diagram?
If you move above that union and then you take intersection,
Uh-huh.
it will be 0 comma 1 by some huge number. Only then
No,
it
no,
would
but
be the intersection.
the intersections don't really stop, right? We are keep
Yeah,
on
yeah,
taking
keep on going.
intersections.
It means like it goes like some kind of sequence.
Yeah, it goes like a sequence. Every time what happens, wherever you have this huge number, I will give you one number
Again,
bigger
I will
than that,
find some other
and then it will
numbers.
become smaller, right?
Yes,
Yeah. So that is why the final intersection is empty.
yes.
So what I was talking about is, suppose an is a sequence of real numbers. Then let us look at these type of sets, minus infinity comma an. Now the question is whether I can take a lim sup inside. Is lim sup n going to infinity minus infinity an equal to minus infinity comma lim sup a? Okay. So what do you think? Is this, are these two sets equal? Sorry. See, we have seen something of this type. The very first example. Let us go back.
Is A an increasing sequence or decreasing sequence?
No, an is any sequence. You don't know whether it is increasing or decreasing.
Yeah, so basically, like if we go by the like definition of lim sup again, so first we have to
Uh-huh.
take the unions of all m greater than equal to n ems. So that will be like minus infinity to am. If we take the unions of all such m greater than equal to n, then that will be like minus infinity to supremum over m greater than equal to n an. And then if we take the intersection of all these sets that all such n's, then that will again give us infimum of supremum of basically
Okay.
n's on the right hand side. And so yeah, so we'll get this equality.
Okay. So your claim is that this is equal, right?
uh,
No, it is fine even if it is wrong.
yeah,
Just tell
I,
me your fine.
yeah, I might have made some mistake. Let me think again. Yeah, so I'm like what I assumed was that if I take unions of all these sets, that's somehow equivalent to taking the supremum of the right hand part of the interval.
Okay. Is it?
No,
Okay, think
actually,
about it. Perhaps, yeah.
yeah, that
Just
may
think
not
about it. What you
be
are
right.
saying.
So suppose if I take ans to be, for example, 1 over n,
Uh-huh.
then minus infinity. Okay, so then lim sup of n 1 over n, that's going to be 0.
Okay.
So I should get minus infinity to 0 on the right hand side of equality, and on the left hand side it will be union of minus infinity to 1 over n, which union of m greater than equal to n minus infinity to 1 over m, which is minus infinity to 1 over n. And then if I take the intersection, it will be minus infinity to closed interval 0. So yeah, so actually, yeah, so here they are not, because I might get a closed interval also on the right hand side from, like on the left side, from the left side of equality, lim sup n approaches infinity minus infinity to n. The interval which I get in the end may not be an open one. Like I might get a
Yes.
closed one also.
So, yeah. So, okay. Whatever he said, is it clear to everyone? Actually, he said quite fast, right?
Yeah, but I think up to boundary points they should be equal. Uh, like it should, the interior of these two sets be the same.
Okay. Just a minute. Let us go slowly. So, what he's saying is there is no guarantee that this is open. No guarantee that this set is open. But the right hand side set is surely open. So in general, there is no guarantee that this is equal. Okay. And what is the example? Example we just saw. Let us look at lim sup minus infinity comma 1 by n. This is minus infinity comma closed zero, which properly contains minus infinity comma 0, which is minus infinity comma lim sup 1 by n. Is this clear? Sashikant and Vishal, is this clear?
Yes.
Yes, sir.
Okay. So now the question is, okay, if this is not equal, can we say that at least this is contained? Like the right hand side is contained in the left hand side. At least can we say this? So what do you think? Can we say this? I mean, Dheeraj already gave some idea, but yeah, just tell me. Sashikant, do you want to try?
No idea, sir. I'm thinking actually.
Okay. What about Vishal?
No, no idea, sir.
Okay, okay. So, okay, let us try to prove this. Let us try to prove that this right hand side is contained in the left hand side. If we are stuck in between, then we might get some idea of counter example. And if we are through, then we are through. So, let us start with some x in this interval. I'm really sorry. I meant to say this interval. Minus infinity to limit lim sup a. So, what does this mean? This means that x is strictly less than lim sup a. And this an is, sorry, lim sup an is nothing but infimum of these supremums. So, okay. Now, what does this imply? Sasikan, can you tell me? If some number is less than the infimum, then what happens?
Number is less than infimum, then I can find a number. Number is less than infimum. No ideas.
See,
I
infimum
mean,
is the
infimum,
greatest.
infimum
No, no,
minus
no.
something, and then infimum there should exist some value.
Okay, see, infimum is the greatest lower bound, right?
Okay.
Infimum is greatest lower bound.
Sir, one small question here. I did
Uh-huh.
not understand that meaning infimum of supremum of AM. Supremum of
Oh,
AM means
see,
A1 to
wait.
AM take maximum value and then A1 to AM plus 1 take again maximum value, so on.
No,
That
wait,
would
wait,
mean
wait.
an increasing
Should
set
I
of all increasing maximum values
let me
and
write
then
the
take again the
definitions?
minimum value.
No, no, no. Wait, wait, wait. Let us first write the definition of supremum, infimum, and everything. Then we'll understand. Do you know what is a lower bound and upper bound?
Yeah, that I know. I mean,
So
infimum of
suppose
supremum is confusing.
you know the definition of infimum and supremum as well.
Yes.
Okay. So okay, that is good. That is good that you know. See, an as such has, you know, it may not have a limit, right? We don't know whether this is a convergent sequence or not. But what I can do, I can talk about the supremum of an. That is the least upper bound. Can I talk about this?
Yes.
Okay. Now, see, where is this
So
supremum taken?
basically, this represents the least upper bound of the sequence. Okay,
Not of
again,
that
if you put,
sequence. This represents the least upper bound of the sequence after a certain stage.
okay, so from A1 to AN, I will take one a maximum value, then A1 to AN plus 1 again take maximum value,
Correct.
and so
So
on.
let us just call this for the time being as small sn. So what
So
is small
after
sn?
AN,
Yes, yes. Tell me. After an,
1 to AN, I will take one maximum value, then 1 to AN plus 1, I will take another maximum value, then I will make a set
No,
Like
no,
that.
no,
Then
no, no.
again take.
See, I am saying, listen, listen. M is bigger than or equal to N. So I am taking, in general, Sn is supremum of an plus 1, an plus 2, and so on. So I'm not taking the first n minus 1 terms. I am taking terms from n onwards.
Okay.
Okay. So can I say that Sn is less than or equal to Sn plus 1? Oh,
Yes.
sorry. No, I cannot say this. Sn is bigger
Sn
than or
greater
equal
than.
to Sn plus, right?
Yes.
See, because this is the supremum of an plus 1, and so on. On the other hand, this is the supremum of an plus 1, and so on. So already every element here is an element here. What can happen is an is bigger than all these elements, right?
Yes. So
So
maximum
Sn
value can
is,
only
yeah.
decrease.
So the supremum can, the supremum will not increase. On the other, so once Sn is now a non-increasing sequence, now I can talk about this infimum. This could be minus infinity as well if it is unbounded below. But this infimum of Sn, this I define as lim sup of A.
Okay.
So do you get the point? That's why I
So
wrote this. Infimum over.
so we have a decreasing frequency and then bounded.
No, we don't know whether it is bounded or not. It could be minus
Sn is a
infinity. It is
Sn is a decreasing sequence, right? Decreasing or constant. I mean non-increasing sequence.
a non-increasing
And then we take minimum value out of that entire set.
of Sn, right?
Yes.
But the thing is, it may not be a real number. It could be minus infinity as well.
Okay.
So this is taken in the sense of extended views. So is this fine now?
Yes, sir.
So similarly, you can define the limit. So that would be supremum of infimum. Okay.
Yes, understood.
So let us go back. Okay. So now what we have? See, infimum is the greatest lower bound, and x is smaller than the greatest lower bound. So can I say that x is a lower bound?
Yes, sir.
Yes, right. So that means uh, this for each n, x is lesser than or equal to, or in fact, x is strictly less than. X is strictly less than supremum over m bigger than or equal to n am. On the other hand, supremum is the greatest upper bound. Sorry, not the greatest upper bound. There is nothing called as a greatest upper bound. The least upper bound, I mean to say. Okay. Now something is less than the least upper bound. It means x is not an upper bound. Is that right?
Yes.
Not an upper bound. But once x is not an upper bound, what does this mean? So I will keep the first quantifier as it is. This means that there is some m bigger than or equal to n, such that x is uh, strictly bigger than am. Uh, what am I right? X is strictly less than am. Correct?
Yes.
Okay. But what does this mean? This means for each n, there is some m such that x is in minus infinity comma am. Right?
Yes.
Now this is just writing intersection n equal to 1 to infinity union m equal to n to infinity minus infinity comma am, but this is equal to the lim sup of minus infinity comma am. Yeah.
Yes.
So, so basically, we have proved this result that lim sup of minus infinity comma an, this contains minus infinity comma lim sup an. And similar question can be asked about limit. So lim in minus infinity comma an, whether it is contained or it contains, we don't know. Minus infinity comma lim in an. So what do you think? Okay, is it fine if I continue for 5 more minutes? Let us complete this and then stop.
Yeah.
Yeah. So what do you think? Which way inequality should hold? See, one expects that whatever happened above should again happen below, right? So we expect that this inequality should hold, correct?
Okay.
So let us see if it is possible or not. We will start the proof. If we get stuck in between, we might get a counterexample. If not, then anyway we are done. So let us start with some x in uh, this thing. Minus infinity comma lim a. So this is same as saying that x is strictly less than lim n. That is the supremum of infimum n bigger than equal to n and n variable or of natural numbers an. Okay. Now, what does this imply? See again, x is less than the least upper bound. It means yes. What does it mean?
It's less than all the upper bounds. Or
That is true. But it means that x is not an upper bound, right?
yes.
Okay. So if x is not an upper bound, it means there is an element inside of this set which is bigger than x. So there is some n such that x is less than, sorry, infimum over n bigger than equal to n a. Is this fine?
Yes.
But now x is less than the greatest lower bound, therefore x is a lower bound, and therefore x is smaller than every am bigger than n. So this means there is some n such that for each m bigger than equal to n, x is less than a. But this is same as writing x is inside the union of the intersection. Correct?
Yes.
So sorry for this confusion between n and m's. So here it is an. Now the question is whether the reverse inequality holds. One expects that it doesn't. So I leave it to you to get a counterexample. Exercise. Check if this limit minus infinity an is contained in minus infinity limit an, and if not, get a counterexample. So actually, we have seen this. You just need to go through the notes and you will get the counterexample immediately. Okay, so perhaps let us stop. There was one more thing which I wanted to do, but we'll do that next time. No issues. So, any questions from today's session?
No, sir.
No? Yeah, Dheeraj and Vishak.
No, sir.
So I guess Dheeraj is not here. Okay, fine. So thank you. We'll meet next time.